The default temperature of the universe is minus 270 degrees Celsius. Not cold the way a January morning is cold. Not cold the way a freezer is cold, or a mountaintop, or the surface of Antarctica in winter. Cold in a way that has nothing to do with weather or season or altitude. Cold as a physical constant. Cold as the answer the universe gives when nothing is fighting against it. Right now, in the room you're sitting in, something is fighting against it. The sun, 150 million kilometers away, is burning 4 million tons of hydrogen per second, and a tiny fraction of that energy has found its way to your planet, into your walls, into the air around your body. Your own cells are burning glucose. The building you're in is probably heated. Everything around you is conspiring, in ways you never think about, to keep you 273 degrees warmer than the universe wants you to be. Stop fighting for a moment. In your mind, let everything go cold. That is what space actually is, not the dramatic freeze of science fiction, where an airlock opens and someone turns to ice in seconds. Something slower, something more patient, something that has been at minus 270 degrees for 13.8 billion years and will be there long after the last star in the observable universe burns out. Tonight we're going to find out what that actually means. Not the poster version, not the textbook summary, the version where the numbers are specific and the physics is settled, and the implications do not stop being strange just because you understand them. The version where a temperature called 2.725 Kelvin, which is the measured temperature of the cosmic microwave background that fills every cubic centimetre of space in every direction you could ever point, becomes something you can feel rather than just file away. Where are you right now? What time is it? Whatever your answer, you are, at this specific moment, a warm thing in a cold universe. One of very few warm things. A temporary exception to a rule that applies everywhere else. Tonight, I want you to understand exactly how cold the rule is, because understanding the cold is not just about physics. It is about proportion. It is about knowing what the universe is actually made of when you take the stars away. It is about sitting with the fact that the space between galaxies, which is most of the space there is sitting at a temperature so close to nothing that the difference is almost philosophical. And here is the part that makes the hair on the back of your neck stand up if you let it. The light from the Big Bang, still travelling, still everywhere, is right now passing through your body. At 2.725 Kelvin, barely above absolute zero, the universe's memory of its own beginning, still radiating, still present, cold enough that you will never feel it no matter how sensitive your instruments get without a room full of expensive equipment to detect it. You're bathed in the afterglow of creation, and it is 270 degrees colder than the air in your lungs. That is where tonight begins. Let me tell you what cold actually is, because the word is doing too much work and most of it is wrong. Cold is not a thing. It is not a substance or a force. It is not something that gets into your bones or seeps through your jacket. Cold is an absence. It is what remains when heat leaves. Temperature, properly understood, is a measure of how fast the particles in a substance are moving. High temperature means fast particles, lots of kinetic energy, lots of collisions. Low temperature means slow particles, less energy, less motion. Absolute zero is the point at which the motion stops entirely, or nearly entirely. Quantum mechanics will not allow a perfect stillness, but as close as physics permits. The scale that captures this honestly is the Kelvin scale. 0 Kelvin is absolute zero. 273 Kelvin is the freezing point of water. 310 Kelvin is the temperature of your body. 5,778 Kelvin is the surface of the sun. The cosmic microwave background, the faint thermal echo of the Big Bang that fills all of space, sits at 2.725 Kelvin, less than 3 degrees above the coldest possible temperature in the universe. In 2003, a team at MIT cooled a cloud of sodium atoms to 0.5 billionth of a Kelvin above absolute zero. Half a nanokelvin. The most extreme artificial cold ever produced. And even that achievement requiring years of precision engineering and laser technology that did not exist a generation ago is still warmer than absolute zero. We have never reached it. In the history of human civilization, with all our physics, we have never produced a single cubic centimetre of matter at absolute zero. The floor is lower than anything we have ever touched. Here is what makes the cosmic background remarkable. The universe itself, the background temperature of open space far from any star or galaxy, sits at 2.725 Kelvin. Not as a record, not as a laboratory achievement, as the natural state of things. The universe is simply that cold, in all directions at all times, as a baseline condition that has existed since the first 380,000 years after the Big Bang, and will continue to exist until the last black hole evaporates billions of trillions of years from now. Heat moves in 3 ways: conduction, through contact, particle to particle; convection, through the flow of a medium, the way hot air rises; radiation, through electromagnetic waves, the way the sun warms your face across 150 million kilometers of nothing. In space, only radiation is possible. There is nothing to conduct through. There is no medium to convect. Every warm object in space loses heat only by radiating it outward as infrared light, and gains heat only by absorbing radiation from something nearby. Far from any star, an object in space radiates its heat outward into the 2.725 Kelvin background and receives almost nothing back. The heat flows out. The temperature drops. It drops slowly because radiation is not an efficient heat transfer mechanism at low temperatures, but it drops without stopping. Every object left alone in the void trends toward 2.725 Kelvin, not because something is pulling it there, because that is what remains when nothing is pushing it higher. You're 37 Kelvin hotter than the surface temperature of the sun's corona as seen from the outside. You're 307 Kelvin hotter than the universe's default. Your warmth is not the norm, it is the exception, and the exception requires constant maintenance. In July of 1969, 3 men in a spacecraft were travelling through a medium with a temperature of approximately 2.7 Kelvin. They were not cold, they were warm, inside a pressurized cabin maintained at shirt-sleeve temperature by a thermal management system that the engineers at NASA had spent years designing and testing. But 12 centimeters of aluminum alloy and insulation separated their warm cabin from a void that was, by every meaningful measure, as close to absolute zero as anything naturally occurring in the solar system. This is the first thing to understand about cold in space. It does not kill you the way cold on Earth kills you. On Earth, cold is a medium. The air conducts heat away from your skin, the wind accelerates the process, water is even faster. Cold on Earth is aggressive. It grabs, it takes. In space, cold is the opposite. It is passive, it waits. In vacuum, heat can only leave through radiation, and radiation at body temperature is slow. An unprotected human being suddenly exposed to the vacuum of space would not freeze solid in seconds the way the movies show it. The cold is not what kills you first. What kills you first is the pressure differential. The dissolved gases in your blood begin to expand. If your lungs are full, they rupture. The moisture on the surface of your eyes and mouth evaporates. You have perhaps 15 seconds of useful consciousness, and somewhere between 1 and 2 minutes before the damage becomes irreversible. Then the cold begins its work. But by then, the other things have already finished theirs. This distinction matters because it tells you something important about what cold in space actually is. It is not an assault. It is an environment. It is the background condition of nearly all the volume in the observable universe, patient and total and completely indifferent to whether anything warm passes through it. The void does not want to freeze you. The void does not want anything. The void just is, at 2.725 Kelvin in every direction, for distances that begin at incomprehensible and scale up from there. Now, consider what happens to an object that survives the other hazards, a spacecraft, say, well insulated, carrying no living crew, placed in a stable orbit far from any star. No propulsion, no power, no internal heat generation. What happens over time? It radiates. It radiates its thermal energy outward as infrared light, slowly, at a rate determined by its temperature and its surface properties. As it cools, it radiates more slowly because cooler objects radiate less energy, but it never stops. Asymptotically, over decades and then centuries, it approaches the background temperature, not quite reaching it, because even 2.725 Kelvin means some radiation arriving from the background, and eventually the object reaches an equilibrium where the tiny amount it absorbs from the cosmic background equals the tiny amount it radiates. At that point, it is done. It is as cold as space itself, as cold as the light from the beginning of the universe. Everything in space, given enough time and enough distance from warmth, ends up here. Every metal, every rock, every lost probe, every dead spacecraft. The cold is patient enough to wait for all of them, and it has been waiting for 13.8 billion years. The moon is the closest natural laboratory for what happens to a solid surface when you take away the protection of an atmosphere. No wind, no weather, no ocean to absorb heat and release it slowly through the night. Just rock and vacuum and the sun and the cold. Depending on where you stand and when, the surface temperature of the moon swings between plus 127 degrees Celsius in direct sunlight and minus 173 degrees Celsius in the lunar night. That is a range of 300 degrees on the same rock, not across different climates or different seasons, across a 2-week cycle from lunar noon to lunar midnight. The Apollo astronauts walked on the sunlit surface in suits that were simultaneously dealing with solar radiation, intense enough to cook them, and the knowledge that one step into shadow would immediately begin a thermal plunge that the suit had to manage. The engineers who built those suits spent years solving a problem with no precedent on Earth, designing a garment that could handle both extremes at once, sometimes on the same person, at the same moment as half the suit was in sun and half was in shadow. But that is the lit surface. The permanently shadowed craters near the lunar poles are something different altogether. These are craters whose geometry and the moon's small axial tilt conspire to keep their floors in permanent darkness. Not seasonal darkness, not temporary darkness, permanent. Sunlight has not touched the floors of some of these craters for billions of years, and in that darkness, without the slightest input of solar energy, the surface temperature has dropped to approximately 40 Kelvin, minus 233 degrees Celsius, colder than liquid nitrogen, one of the coldest natural environments in the inner solar system. In those craters, water ice has been accumulating for the entire history of the moon. Delivered by comets and asteroids over billions of years, each impact adding a little to the deposit, the ice never sublimating because nothing has ever been warm enough to sublimate it. The molecules in those ice deposits have been frozen in place since before complex life existed on Earth. They have been sitting at 40 Kelvin, perfectly still, for 3 billion years. Scientists want to mine this ice. It could be split into hydrogen and oxygen for rocket fuel. It could provide water for lunar bases. But before any of that, it is something else. It is a record. A pristine chemical archive of the early solar system, preserved in cold so absolute that not even time has managed to disturb it. Cold, at sufficient extremes, stops being a killer and becomes a preservative. The permanently shadowed craters of the Moon contain the solar system's oldest unopened letters, sealed in ice at 40 Kelvin, waiting for someone with the tools and the patience to read them without destroying what they find. The cold that makes those craters unreachable is the same cold that makes them irreplaceable. The vault and the obstacle are the same thing. Two objects, one in sunlight and one in permanent shadow, sitting a few kilometers apart on the same world. A 300-degree difference. Both of them, by any terrestrial standard, extreme. But the permanently shadowed craters are the ones that hold the memory, the ones that show you what the solar system looked like before the sun had a chance to interfere. Mars is the planet we talk about most when we talk about going somewhere. It is the destination in almost every serious conversation about human expansion beyond Earth, and it is genuinely more hospitable than anywhere else we could reach in a reasonable time frame. But hospitable by the standards of the solar system is not the same thing as hospitable by any standard a human body was designed for. The average surface temperature on Mars is minus 60 degrees Celsius. Average. That includes the warmest days at the equator in midsummer, when noon temperatures near the equator can briefly touch 20 degrees Celsius. Warm enough to feel almost pleasant if you were somehow standing there in the right gear at the right moment. But the average includes everything else too. The nights, which drop to minus 90. The poles in winter, which touch minus 125. The pre-dawn hours at any latitude, where the thin atmosphere has had an entire Martian night to radiate whatever heat it absorbed during the day. The atmosphere is the key to understanding Martian cold. It is there, which Mars has over the Moon, but it is thin. About 0.6% of Earth's atmospheric pressure at the surface. Thin enough that it provides almost no thermal blanket. On Earth, the atmosphere traps heat overnight. Coastal cities at the same latitude as polar deserts are 30 degrees warmer because the ocean and the air hold the heat. Mars has neither. The thin atmosphere bleeds its heat back to space almost as fast as the sun puts it in. The result is a temperature swing that would destroy most mechanical systems not specifically engineered to survive it. The InSight lander, which operated on the Martian surface from 2018 until 2022, measured temperature swings of 80 to 100 degrees in a single Martian day. Every day. The electronics survived because they were specifically designed to survive it, housed in a thermally insulated enclosure and heated when necessary. Without that engineering, the electronics would have failed within weeks. Now, a human body. The human body operates within an extraordinarily narrow temperature range. Core temperature needs to stay within a few degrees of 37 Celsius, or the machinery starts to fail. The brain is the most vulnerable. Hypothermia begins at a core temperature drop of just 2 degrees. At a drop of 5 or 6, the ability to make decisions and take actions to warm yourself is already compromised. At a drop of 10, you are in serious danger. At 15 degrees below normal, the heart begins to fail. A person on the Martian surface, unprotected, would lose consciousness to hypoxia in under 2 minutes from the lack of breathable atmosphere. But the cold would be working the entire time they were still breathing. At minus 60, exposure would accelerate the shutdown of peripheral circulation, sending blood to the core, shutting down the extremities, preserving the vital organs for as long as possible while the surface of the body froze. Mars is the easy planet. This is what the easy planet offers. The further out you go from the sun, the worse it gets. Mars is a prelude to a cold that makes minus 60 feel like a mild inconvenience. Pluto sits at an average distance of about 39 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, roughly 150 million kilometers. So Pluto orbits at approximately 5.9 billion kilometers out. At that distance, the Sun is not the blazing disk it appears from Earth. It is a bright star, brilliant by stellar standards, but a point of light, not a sun. The solar flux at Pluto's surface is about 1,600 times weaker than it is on Earth. The surface temperature of Pluto is approximately 44 Kelvin, minus 229 degrees Celsius. At 44 Kelvin, nitrogen is a solid. Not a gas, not a liquid, a solid. Pluto has glaciers made of frozen nitrogen that flow across its surface under their own weight, behaving geologically the way ice behaves on Earth. The largest of these, a vast pale plain called Tombor Regio, is resurfaced continuously by the flow and sublimation of nitrogen ice, which is why it shows almost no impact craters. At 44 Kelvin, nitrogen ice is soft enough to flow. Everything else, including water, is frozen hard as granite. The mountains that surround Tombor Regio are made of water ice. At 44 Kelvin, water ice has the mechanical properties of rock. It stands in peaks 3 kilometers high. It holds its shape over geological time. It is not slippery. It does not melt. It is simply a mineral, one of several solid substances that make up the geological surface of a world most of us still think of as a minor footnote at the edge of the solar system. When New Horizons flew past Pluto in July 2015, after 9 years of travel, after traversing more than 5 billion kilometers, what it found was not the dead, featureless ball of ice that many had expected. It found a world, active geology, a haze atmosphere extending 200 kilometers above the surface. Mountains, plains, possible cryovolcanism, a world shaped by the tension between the tiny warmth of a distant star and the deep cold of space. And beneath all of it, beneath the nitrogen glaciers and the water ice mountains and the methane frosts possibly, an ocean. Not a frozen shell around a rock, an actual liquid water ocean, maintained by the residual heat of radiogenic decay in Pluto's rocky core, insulated by the ice above it, never having seen sunlight in the 4.5 billion years since it formed. If it exists, and the evidence points toward it, it is liquid water at temperatures hovering just above freezing, in complete darkness, under pressures that would crush unprotected humans, isolated from any energy source except the slow decay of radioactive elements in the rock below. In the coldest confirmed environment in the solar system, there may be liquid water. Cold is not the opposite of complexity. Cold is what you find everywhere that complexity is not being actively maintained by something warm. And sometimes, deep enough under the cold, hidden from the cold by the cold itself, the warmth persists anyway. Voyager 1 was launched on September 5th, 1977. It has been travelling ever since. As of 2024, it is approximately 23.5 billion kilometres from the Sun, more than 157 times the distance from the Earth to the Sun. It crossed the heliopause, the boundary where the solar wind gives way to interstellar space, in 2012. It is now, by any reasonable definition, in the space between the stars. It is moving at roughly 17 kilometers per second. Fast. Enormously fast by any human scale. At that speed, it takes Voyager about 10 hours to cover the distance between Earth and the Moon. But at that same speed, travelling toward the nearest star system, Alpha Centauri, Voyager 1 would take approximately 73,000 years to arrive. And Voyager 1 is not even travelling in that direction. There is a temperature in the region where Voyager 1 now travels. The local interstellar medium, the thin soup of gas and charged particles that fills the space between stars, has a temperature of roughly 30,000 Kelvin. This sounds hot. It is not hot in any way that would matter to you. Temperature, remember, is a measure of the average kinetic energy of particles. The interstellar medium has particles moving at speeds corresponding to 30,000 Kelvin, but the density is approximately 0.1 particles per cubic centimetre. For comparison, the air in the room you're sitting in has about 27 quintillion particles per cubic centimetre. The interstellar medium has one particle, where the air around you has 270 quintillion. Those particles are moving fast, but there are so few of them that they carry almost no heat in any practical sense. If you placed an object in the interstellar medium, it would not warm to 30,000 Kelvin. It would radiate its heat outward and slowly cool toward the cosmic background temperature, because there is nothing to warm it. The particles are too sparse to transfer heat meaningfully. This is the distinction between temperature and thermal content that almost never gets explained properly, and it is the distinction that makes the interstellar medium genuinely cold despite its nominal temperature. High temperature, almost no thermal mass, nothing to warm you. The cold of deep space is not just a matter of low temperature, it is the absence of anything carrying enough heat to transfer. Voyager 1 carries a radioisotope thermoelectric generator, a nuclear battery that converts the heat of decaying plutonium-238 into electricity. It was producing about 470 watts when launched. It produces less now, as the plutonium decays. It will eventually go silent, perhaps within the next few years, and when it does, the spacecraft will cool. Slowly, because it is well insulated, and because radiation in the direction of space is a slow process at these temperatures, but inexorably. Over decades, it will approach the temperature of the space around it, a temperature that is, in this part of the interstellar medium, defined not by the local plasma, but by the cosmic microwave background that fills all of space equally. 2.725 Kelvin, the same temperature in the interstellar medium beyond the heliopause as it is in the void between galaxy clusters, the same temperature it has been since the universe was 380,000 years old. Voyager 1, silent, cold, carrying a golden record encoded with the sounds of Earth, will drift through that temperature for longer than the Earth has been a planet. The interstellar medium is not empty. People say space is empty, and in a colloquial sense it is. But the interstellar medium is a complex structured environment. It has phases, it has chemistry, it has magnetic fields that stretch across light years, it has regions of compression and expansion, clouds of gas that collapse under gravity to form stars, expanding shells of material blasted outward by supernovae. It is not nothing, but most of it is extraordinarily cold. The warm phases, the ionized gas near hot stars, the regions heated by supernova shockwaves are local and temporary. The dominant phase of the interstellar medium, the one that occupies most of the volume, is what astronomers call the cold neutral medium. Temperatures of 50 to 100 Kelvin, densities of 20 to 50 atoms per cubic centimetre, vast clouds of atomic hydrogen, drifting, slowly cooling, occasionally dense enough in some regions to shield the inner gas from ultraviolet radiation and allow molecules to form. Those molecular regions, the coldest and densest parts of the interstellar medium, have temperatures of 10 to 30 Kelvin. They are called molecular clouds, and they are where stars form. Giant complexes of hydrogen, dust and trace organic molecules stretched across tens of light years, slowly contracting under gravity. The Orion molecular cloud, the birthplace of the stars in the Orion Nebula, has a temperature in its dense cores of about 10 Kelvin, minus 263 Celsius, less than 10 degrees above absolute zero. And yet, in those cores, chemistry happens. Over 200 distinct molecules have been detected in interstellar molecular clouds: formaldehyde, methanol, acetic acid, glycolaldehyde, a simple sugar, amino acid precursors, complex carbon chains that form the building blocks of organic chemistry. All of it assembled, molecule by molecule, at temperatures close to absolute zero, on the surfaces of dust grains where atoms can stick and react over millions of years. This is one of the most counterintuitive facts in all of astrochemistry. The cold is not sterile. The cold is, in a specific and important sense, productive. The chemistry of life did not begin on a warm primordial Earth. It began in the coldest, darkest regions of the interstellar medium, on dust grains at 10 Kelvin, over timescales of millions of years, long before the solar system existed. Every carbon atom in your body, every nitrogen atom, every complex organic molecule that eventually wound up in the chemistry of living cells, passed through something cold first. Probably through something very cold. Through something 10 degrees above absolute zero in the dark between stars. Life, it turns out, is made of material that assembled itself in the deep freeze. The warmth we associate with life, the 37 degrees of a living body, the 15 degrees of a temperate biosphere, these are not where life's chemistry was invented. They are where it was deployed. The invention happened in the cold. The patents were filed in molecular clouds at 10 Kelvin, over timescales the human mind cannot genuinely hold. That is what the interstellar medium actually is. Not empty, not just cold. A vast, dark, slow chemical factory producing the raw materials of complexity in conditions that would kill any finished product of that complexity in seconds. The Boomerang Nebula is the coldest natural object in the observable universe. Colder than the cosmic microwave background, colder than the void between galaxy clusters, the coldest thing that physics, operating without human intervention, has managed to produce. It sits about 5,000 light-years from Earth in the constellation Centaurus. It is a preplanetary nebula, the outer layers of a dying star being expelled into space as the star's fuel runs out, and the outer envelope expands outward. All dying stars go through something like this. What makes the boomerang unusual is the speed at which the material is expanding. About 164 kilometers per second, faster than almost any other outflow from a dying star. When a gas expands rapidly, it cools. This is not mysterious. It is thermodynamics. The expanding gas does work on its surroundings, and the energy for that work comes from the thermal energy of the gas itself. Expand fast enough, and the cooling is dramatic. The gas in the Boomerang Nebula has expanded fast enough that its temperature has dropped below the cosmic microwave background. 1 Kelvin. 1 degree above absolute zero, in a natural object, without human engineering, without laser cooling or magnetic traps, just physics, operating on a dying star's expelled outer layers at a speed that violates intuition but not equations. The Hubble Space Telescope has imaged the Boomerang Nebula. In the images it is almost comically gentle looking. A soft blue glow, hourglass-shaped, symmetric, the kind of object that gets used in science communication pieces about the beauty of the cosmos. And it is beautiful. It is also 1 degree above the coldest possible temperature in the universe, outpacing in its coldness the background radiation of the Big Bang itself. The cosmic microwave background, that 2.725 Kelvin bath of ancient photons, passes through the Boomerang Nebula and is absorbed by it, because the nebula is colder. The background is giving its heat to the nebula. The faint echo of the universe's beginning is warming a dying star's outer layers. This will not last. The nebula will continue to expand. As it expands, it will spread out and thin, and eventually the opacity that traps the background radiation will decrease, and the cooling effect will diminish. Eventually the nebula will warm back to the background temperature. The coldest known object will merge back into the ordinary cold of space. But for now, at this moment in the history of the universe, It sits at 1 Kelvin. Below the floor, colder than space itself. The universe produces extremes in all directions. It produces the surfaces of massive stars at 50,000 Kelvin. It produces neutron star cores at billions of Kelvin. It produces the centers of black holes at conditions our equations cannot describe. And it produces quietly in a nebula 5,000 light-years away a gas at 1 Kelvin. The coldest thing there is. The thing that cold becomes when given the right conditions and enough time and a dying star willing to expel its outer layers at 164 kilometers per second into the patient dark. Here is the number that should recalibrate everything else in tonight's conversation. 2.725, not minus 270, not close to absolute zero, 2.725 Kelvin. That is the temperature of the cosmic microwave background, the thermal radiation left over from the Big Bang, filling all of space, arriving from every direction equally, a consequence of physics that has been operating since 380,000 years after the moment of creation. When the universe was young, it was hot, unimaginably hot. The first fractions of a second were at temperatures measured in the billions of Kelvin, conditions under which matter as we know it could not exist, under which protons and neutrons could not hold together, under which space itself was a seething plasma of quarks and gluons. It has been cooling ever since. 13.8 billion years of expansion have stretched the universe's fabric, and as space expands, radiation redshifts, and as radiation redshifts, it cools. The universe began at incomprehensible heat, and has been cooling toward cold at a rate determined by the expansion of space itself. What we measure as the cosmic microwave background is a photograph of that cooling, taken when the universe was 380,000 years old and had cooled enough for electrons to combine with protons and form neutral hydrogen, making the universe transparent for the first time. The light released at that moment has been travelling freely ever since, stretched, cooled, now arriving at 2.725 Kelvin from every direction at once. It is passing through you right now, not metaphorically. The cosmic microwave background is a bath of photons with a temperature of 2.725 Kelvin that fills the entire observable universe, including the room you're in. It passes through walls. It passes through your body. It is arriving at every point in your skin from every direction simultaneously, at a flux too low to detect without dedicated equipment, at a temperature so close to nothing that the word cold feels inadequate. You're surrounded at every moment of your life by the afterglow of the Big Bang. You always have been. You have never not been bathed in the oldest light in the universe. It is just that 2.725 Kelvin is so cold relative to the thermal noise of your environment that you've never had any reason to notice it without specifically looking for it with very good instruments. The Planck satellite launched in 2009 mapped this background in extraordinary detail. It found temperature fluctuations of about 1 part in 100,000. Regions slightly warmer or slightly cooler than average. Variations that correspond to slight density differences in the early universe. Differences that grew under gravity over 13 billion years into the galaxies and galaxy clusters and cosmic web we see today. The entire large-scale structure of the universe, every galaxy that has ever formed, every star that has ever burned, every planet that has ever existed, grew from tiny ripples in the temperature of a 2.725 Kelvin thermal bath. The cold is not just the background, the cold is the canvas everything is painted on. There is a process at work in the universe that will eventually produce a cold more complete than anything so far described. It has a name. Physicists call it heat death. The second law of thermodynamics says that entropy, the measure of disorder in a closed system, always increases or stays the same, never decreases. This is not a tendency or a statistical preference. It is a law, the most fundamental constraint on the direction of time. You can build a refrigerator and make one small part of the universe colder, but only by making another part warmer, and only by consuming energy from somewhere else. The total entropy goes up. It always goes up. For the universe as a whole, this means one thing. Eventually, everything equalizes. Eventually, the temperature differences that drive every process in the universe, the temperature difference between the core of a star and empty space that drives nuclear fusion, the temperature difference between the surface of a planet and its dark side that drives weather, the temperature difference between a living cell and its surroundings that drives metabolism, all of these differences eventually vanish. Not tomorrow, not in 1 billion years, not in 1 trillion years, but eventually. Given time on the scale that the universe itself operates, the heat death of the universe is not a dramatic event. There is no explosion, no collapse, no final catastrophe. It is the slow, patient equalization of temperature across the entire observable universe until every region is the same temperature. And that temperature, at the end of heat death, will be essentially absolute zero, not the 2.725 Kelvin of the current cosmic background. Less. The universe will continue to expand. As it expands, the background radiation cools further. The last stars will burn out in roughly 1 quadrillion years, 1 with 15 zeros. The last stellar remnants, white dwarfs and neutron stars, will cool to the background temperature on timescales far longer. Black holes will evaporate through Hawking radiation on timescales that make the current age of the universe look like a morning. And after the last black hole is gone, there will be nothing left radiating, nothing left with excess energy. The temperature will fall and fall, arbitrarily close to absolute zero, never quite reaching it, because the expansion of space itself maintains a residual background radiation, but approaching it. Always approaching it. The heat death is not the end of the universe. The universe goes on. It just goes on in a state where nothing can happen, where no process is possible, because all processes require a temperature difference, and all temperature differences have equalized. The universe becomes, in the most complete sense, cold. This is where everything is going. Every warm thing you have ever touched, every fire you have ever seen, every star visible in the night sky, everything that has ever radiated heat and light is moving toward this end state. Not quickly, but without exception. The cold does not hurry because the cold has forever. And you, reading this right now, are one of the temporary warm things, one of the brief interruptions in the universe's long slide toward cold. The interruption is real. The warmth is real. The cold is patient. In 1995, at Gila in Boulder, Colorado, a team led by Eric Cornell and Carl Wieman cooled a cloud of rubidium atoms to 170 nanokelvin above absolute zero, 170 billionths of a Kelvin. At that temperature, the atoms stopped behaving as individual particles and collapsed into a single quantum state, a phenomenon Einstein and Bose had predicted in the 1920s and that physicists had been trying to produce ever since. They had made the coldest thing on Earth, and possibly the coldest thing in the local universe at that moment. What happened when they got there was genuinely strange. At temperatures this close to absolute zero, the quantum mechanical nature of matter stops being a background detail and becomes the dominant reality. The atoms were no longer atoms in any practical sense. They were a collective quantum object, all occupying the same quantum state, all described by the same wave function. The boundary between particles dissolved. The gas became something between a collection of particles and a single entity, a Bose-Einstein condensate. This is what cold does to matter at sufficient extremes. It does not just slow things down, it changes what they are. The rules that govern matter at room temperature, the rules that make particles discrete and distinguishable and subject to classical mechanics, those rules fail at temperatures close to absolute zero. Quantum mechanics takes over entirely. Matter begins to behave in ways that have no analogue in everyday experience. Superfluid, superconducting, exhibiting coherence across macroscopic distances, flowing without resistance, tunneling through barriers that classical mechanics would call impassable. The coldest environments in the universe, the Bose-Einstein condensates in physics laboratories on Earth, the interiors of neutron stars where neutrons may enter a superfluid state, are also the places where physics is most strange. The familiar rules only hold at temperatures warm enough to wash out the quantum effects. Get cold enough, and the weirdness comes through. But the laboratory coldness of 170 nanokelvin is something we made. We built it. We cooled atoms with lasers and magnetic fields down to temperatures that do not occur naturally anywhere in the known universe outside of Bose-Einstein condensate experiments. In all of interstellar space, in all the cold molecular clouds and the permanently shadowed craters and the Boomerang Nebula, there is nothing at 170 nanokelvin except what humans have deliberately created. The coldest things in the known universe are things we built. That says something about the relationship between intelligence and cold. Cold is the natural state. Warmth requires maintenance. But the deepest cold, the coldest cold, the temperatures that do not occur anywhere in nature, require even more maintenance than warmth. They require the most sophisticated technology our civilization has produced. Laser cooling, magnetic traps, supercooled environments, the complete isolation of a small number of atoms from every thermal influence in their surroundings. The most extreme cold and the most extreme warmth are both artifacts of intelligence. Nature occupies the middle ground. We live at both edges. The most extreme cold and the most extreme warmth are both, in different ways, products of intelligence pressing against what the universe offers by default. The natural cold of deep space is 2.725 Kelvin. The engineered cold of the Boulder laboratory is 170 nanokelvin. The gap between those two numbers is the distance intelligence has travelled in the direction of cold. It is not a small distance. The International Space Station orbits Earth at roughly 400 kilometers altitude, completing one orbit every 90 minutes. 16 times per day, it crosses from sunlight into the shadow of the Earth and back again. Each crossing takes about 45 minutes in shadow, 45 minutes in light. During those 45 minutes in sunlight, surfaces facing the sun reach temperatures around 121 degrees Celsius. During the 45 minutes in shadow, those same surfaces drop to about minus 157 degrees Celsius, a swing of almost 280 degrees in 90 minutes. Repeated 16 times per day, every day, for years. The engineers who designed the station's thermal control system had to solve a problem that is, in some ways, the central engineering problem of human spaceflight. Not how to get warm enough. How to manage a thermal environment that is trying to simultaneously cook and freeze you, depending on which way you are pointing, at intervals of 45 minutes. The solution is a combination of passive and active systems. Passive systems include multi-layer insulation blankets, surface coatings with specific reflectivity properties, and the geometry of the station itself, designed to spread thermal loads. Active systems include fluid loops that carry heat from where it is generated, primarily the electronics and the crew metabolism, to large radiator panels that dissipate it into space. The loops use ammonia as the working fluid, because ammonia remains liquid across the full range of temperatures the system experiences. The crew inside experiences none of this. The habitat modules are maintained at between 18 and 27 degrees Celsius. The thermal control system is so effective that the astronauts feel the same range of temperatures as in a slightly variable office building. The profound thermal hostility of their actual environment, swinging 280 degrees every hour and a half, is invisible to them. It is managed by systems they rely on without thinking about, the way you rely on your body's thermoregulatory system without thinking about it. But during spacewalks, the engineering challenge becomes personal. Astronauts conducting extravehicular activities are protected by their spacesuits, which are themselves miniature thermal management systems. The outer layers have specific reflectivity to reject solar radiation. Inner layers of insulation prevent heat loss to the vacuum. A liquid cooling and ventilation garment worn directly against the skin removes metabolic heat generated by the physical effort of working in the suit. The suit has to manage two opposite risks simultaneously. Get it wrong in one direction, and the astronaut overheats from their own metabolic output with nowhere for the heat to go. Get it wrong in the other direction, and the cold of space just outside the suit wall finds a way in. The margins are not as wide as the engineering makes them appear. The suits work because they were designed by people who understood precisely what was waiting on the other side of the material. The cold is always there, 1 centimetre away, 280 degrees below the air in your lungs, always waiting for the engineering to fail. Hypothermia is not what most people think it is. The death from cold is not the Hollywood version, the body going stiff and still as the temperature drops and the heart quietly stops. It is stranger than that, more insidious, more willing to be mistaken for something else until it is too late. The human core body temperature is 37 degrees Celsius. The first sign of trouble comes at 35, a drop of 2 degrees. At 35, the thinking becomes impaired in ways that feel, to the person experiencing it, like normal thinking. The judgment is degraded, but the confidence in that judgment is not. Cold people make bad decisions about how cold they are. This is the first cruel trick. The very faculty needed to recognize the emergency is the first one compromised. At 32 degrees, shivering sometimes stops. This feels like improvement. It is the opposite. Shivering is the body generating heat through involuntary muscle contractions. When it stops, it is because the body has run out of the metabolic resources to maintain it, not because the situation has resolved. The cessation of shivering is often the step before the final decline. At 28 degrees, the heart becomes prone to arrhythmias. Ventricular fibrillation, the chaotic quivering of the heart muscle that provides no effective circulation, can be triggered by even small disturbances, including the movement of the patient during rescue. People have died during rescue from hypothermia because their rescuers moved them before the core temperature was stable enough to tolerate the manipulation. Below 24 degrees, consciousness is lost. Below 18, the heart stops spontaneously. And yet, people have been resuscitated from core temperatures as low as 13 degrees Celsius. There is a phrase in emergency medicine, not dead until warm and dead. Because the same cold that shuts the body down also slows the damage from the shutdown. The brain, starved of oxygen when the heart stops, would be permanently damaged in 4 minutes at normal temperature. At 18 degrees, the same brain can survive without circulation for far longer. The cold that kills also preserves in a way that is exploited in some surgical procedures where patients are deliberately cooled to allow operations that would be impossible otherwise. Cold is not simply destructive. It is a regulator of biological rate processes, including the rate of dying. In space, none of this applies in any practical sense. A person exposed to the vacuum dies from decompression and anoxia long before hypothermia becomes the primary threat. But the underlying biology is worth understanding. because it tells you something important about the relationship between warmth and life. Life is not just compatible with a narrow temperature range. Life is, in a deep sense, constituted by that temperature range. The enzymes that drive biochemistry work at 37 degrees because they evolved at 37 degrees. Go significantly above or below, and the machinery fails, not gently, catastrophically. The 2-degree margin between normal and early hypothermia is not a safety buffer. It is an early warning sign that the engine is already beginning to struggle. The human body is not tolerant of cold. It is defended against it by a thermoregulatory system that spends a remarkable fraction of its metabolic resources keeping the core within the narrow range where the chemistry works. When that defense fails, when the resources run out or the cold overwhelms the defense faster than the defense can respond, the failure is progressive and largely irreversible. The universe runs at 2.725 Kelvin. Your body runs at 310. The distance between those two numbers is life. Aerogel looks like a solid. Under certain lighting conditions, it looks faintly blue. It is produced by extracting the liquid from a gel and replacing it with gas without allowing the solid structure to collapse. What remains is a material that is roughly 99% air by volume. A cubic centimetre of aerogel contains mostly nothing, held in a structure so intricate that the holes in it are smaller than the mean free path of air molecules at minus 200 degrees Celsius, at minus 250, at temperatures approaching absolute zero. In the Mars rovers, the electronics sit inside warm electronics boxes lined with aerogel. Outside the boxes, the Martian night drops to minus 90. Inside, the temperature stays warm enough for the circuits to operate. The aerogel is the difference between a functioning rover and a very expensive piece of frozen scrap metal. The same idea, in more extreme form, applies across every spacecraft ever built. The problem with thermal management in space is not just the cold, it is the vacuum. On Earth, even at very low temperatures, there is air. Air conducts heat from warm surfaces to cold ones. It convects, moving warm and cool masses around in a way that tends to equalize temperatures across distances. In space, there is no air. There is only radiation. And radiation, as a heat transfer mechanism, is slow and one-way at low temperatures. The challenge is not keeping things from freezing. The challenge is controlling precisely where heat goes and where it does not. The James Webb Space Telescope illustrates this beautifully. Webb needs to observe infrared light from the earliest galaxies in the universe. To do this, its mirrors and sensors need to be cold, not a little cold. Cold enough that the telescope itself does not glow in the infrared wavelengths it is trying to detect. The instruments need to sit below 50 Kelvin. Some of them need to be below 7 Kelvin. Webb sits at the L2 Lagrange point, 1.5 million kilometers from Earth. It carries a sunshield the size of a tennis court, 5 layers of Kapton film coated with aluminum, each layer separated by a vacuum gap. On the side facing the sun, the outer layer reaches about 85 degrees Celsius. On the cold side, behind 5 layers of Kapton, the temperature drops to below minus 230 Celsius. One side of a tennis court at a temperature humans could work in, the other side at a temperature lower than the Martian poles in winter, separated by 5 thin layers of coated plastic and the insulating vacuum between them. The mid-infrared instrument MIRI needs to go even colder, below 7 Kelvin. An active cryocooler, a small mechanical refrigerator driven by electrical power, runs continuously to pump heat out of MIRI and keep it at the temperature necessary to see faint infrared light from galaxies 12 billion light-years away. Remove the cryocooler and MIRI warms. Remove the sunshield and the entire telescope warms. The cold of the instrument is maintained by engineering, not by the environment. The environment, Even 1.5 million kilometers from Earth would allow Webb to warm far above its operating temperature if the sunshield were not there blocking the sun. Cold, at the temperatures where the most interesting physics happens, is something you build and maintain, not something you find. Saturn is almost 10 times farther from the Sun than Earth is. Jupiter is 5 times farther. Uranus and Neptune are 19 and 30 times farther respectively. As you move outward through the solar system, the Sun's light weakens with the square of the distance. At Saturn's orbit, the Sun delivers about 1% of the energy per square meter that it delivers to Earth. At Neptune, about 0.1%. The consequences for temperature are direct. Saturn's cloud tops average about minus 178 degrees Celsius. Uranus and Neptune, despite being similar in composition, have different internal heat sources and wind up at minus 224 and minus 201 degrees Celsius respectively. These are not edge cases or extreme conditions. These are average atmospheric temperatures on the largest worlds in the solar system. Half the solar system by mass, the 4 gas giants, orbits at temperatures where most substances familiar from everyday life are solid. But the most interesting cold in the outer solar system is not the atmospheric temperature. It is what happens underneath. 3 moons in the outer solar system are known or strongly suspected to have liquid water oceans beneath their surfaces. Europa, orbiting Jupiter, is covered by a smooth ice shell roughly 10 to 30 kilometers thick, under which an ocean of liquid water may contain twice as much water as all of Earth's oceans combined. Enceladus, orbiting Saturn, actively erupts plumes of water vapor and ice from beneath its south pole, direct evidence of a liquid ocean maintained by tidal heating from Saturn's gravity. Titan, Saturn's largest moon, may have a liquid water ocean beneath its surface and has liquid methane and ethane lakes and seas on its surface, the only known stable surface liquids in the solar system apart from Earth. In all 3 cases, the warmth that maintains these oceans is not solar. The Sun is too far away and too weak. The warmth is internal. Tidal heating, the frictional dissipation of tidal forces as the moons are kneaded by their parent planet's gravity. Radioactive decay, the slow release of heat from heavy elements in the rocky interiors. These are modest heat sources. They maintain modest warmth, but they are enough, in the insulating embrace of thick ice shells, to keep liquid water from freezing. The outer solar system, so cold at its surface that nitrogen and methane are frozen solid, contains multiple liquid water environments hidden beneath the ice. The cold is not uniform. The cold at the surface is real. The warmth beneath it is also real. The universe is arranged for these 2 things to coexist through the specific geometry of tidal heating and thick insulating ice. This is why the search for life in the outer solar system is not obviously futile. The surface temperatures are incompatible with life as we know it. The subsurface temperatures potentially are not. If you're looking for the warm places in the cold solar system, you look down, not up. You look under the ice. When a sufficiently massive star exhausts its nuclear fuel, what remains is a neutron star. The outer layers are blown off in a supernova explosion, and the core collapses under its own gravity until the protons and electrons are forced together, forming neutrons, and the neutron degeneracy pressure halts the collapse. What you are left with is roughly 1.4 times the mass of the Sun packed into a sphere about 20 kilometers across. The density at the core is higher than the density of an atomic nucleus. A teaspoon of neutron star material would weigh several billion tons on Earth. At the moment of formation, the neutron star is extraordinarily hot. The interior temperature reaches perhaps 100 billion Kelvin in the first seconds, the hottest environment in the universe apart from the conditions immediately following the Big Bang. Neutrinos carry away most of this energy in minutes. The surface cools to about 1 million Kelvin within a year, still emitting primarily in X-rays, glowing in wavelengths our eyes cannot see. Over thousands of years, the surface temperature drops through the hundreds of thousands of Kelvin range. Over millions of years, through the tens of thousands. An old neutron star, if undisturbed, if not accreting material from a companion, cools slowly toward the background temperature, not quickly. The specific heat of neutron star material and the thermal conductivity of the crust control the rate, and the physics is unusual and not fully understood, involving the possible superfluidity of the neutron interior at low temperatures. But the direction is always the same, toward cold. A neutron star that has been cooling for 10 billion years, roughly the age of the oldest stars in the Milky Way, is at temperatures in the range of a few thousand to a few tens of thousands of Kelvin, still warm, still emitting faintly in ultraviolet and X-ray. But the trajectory is clear. Given enough time, neutron stars cool too. Black holes are different. A black hole, in classical general relativity, is cold in the most absolute sense possible. It emits nothing. No radiation, no particles, nothing. It only absorbs. By classical physics, a black hole has a temperature of absolute zero, or rather, a temperature that is undefined because a black hole has no thermal radiation. Stephen Hawking showed in 1974 that this is not quite right. Quantum mechanics applied to the geometry of the event horizon predicts that black holes do emit radiation, an effect now called Hawking radiation, arising from quantum fluctuations near the horizon. The temperature associated with Hawking radiation is inversely proportional to the mass of the black hole. For a stellar mass black hole, the temperature is about 0.000000006 Kelvin, 60 nanokelvin, less than 1/10,000,000th of a Kelvin, colder than any laboratory has achieved, colder than the cosmic microwave background. The most massive, most violent objects in the universe are also the coldest. A black hole is not hot. A black hole is almost absolutely cold, bathed in a universe that is, at 2.725 Kelvin, warmer than it is. The universe is heating the black hole. The black hole is barely radiating back. Eventually, as the universe cools, as the cosmic background temperature drops below the Hawking temperature of even the largest black holes, they will begin to evaporate. Slowly, over timescales that make the current age of the universe look like a Planck time. But they will evaporate. The cold wins, in the end, even against a black hole. The question of how cold space is connects eventually to the question of what happens to things left in space for a very long time. Voyager 1 will not last forever. The metal will not corrode in the way it would on Earth, because there is no oxygen, no water, no biological activity to cause decay. But the radiation environment of interstellar space is not benign. Cosmic rays, high-energy charged particles accelerated to near-light speed by supernova and other energetic events, continuously bombard everything in their path. Over millions of years, cosmic ray bombardment slowly disrupts chemical bonds, causes radiation damage in materials, alters surface compositions. The golden record aboard Voyager, intended to last billions of years, will eventually be degraded beyond readability by cosmic ray damage, though the timescale is long enough that it is not a practical concern. The spacecraft will cool. The materials it is made of, aluminum and titanium, and gold and various polymers, will all eventually reach the temperature of the surrounding interstellar medium, a temperature defined, as we have established, by the cosmic microwave background, 2.725 Kelvin. At that temperature, the thermal properties of the materials are unlike anything we measure in laboratories. Metals near absolute zero can exhibit superconductivity, the complete disappearance of electrical resistance. Some become more brittle. Some exhibit quantum effects that are irrelevant at room temperature. None of this will matter for Voyager. The electronics will long since have failed, the plutonium will have largely decayed, the antenna will have been slightly deformed by decades of thermal cycling from the occasional warming when it was still in the solar system and the absolute cold of the interstellar medium. But the structure will persist. The mass will be there, drifting through interstellar space, cold, dark, silent. In roughly 40,000 years, Voyager 1 will pass within about 1.7 light-years of a star called Gliese 445, not close enough to be gravitationally captured, close enough that the star might, from the right angle, be recognizable as a slightly brighter point against the background stars. The spacecraft will continue past without slowing. No one will be there to observe it. No message will be received from it. It will simply drift past a star, cold and silent, on its way to wherever the galaxy's rotation and gravitational dynamics eventually carry it, billions of years from now. Cold preserves. The spacecraft that visited the outer solar system, that sent back the photographs of Saturn's rings and Jupiter's clouds and the volcanic eruptions of Io, will persist in some form for longer than the sun has been burning. The mission lasted 50 years. The artifact will last geological ages, drifting through cold that is so complete and so uniform that even time, as a force of change, barely operates. Cold does not destroy. Cold suspends. This is perhaps the most important thing about the cold that the word cold does not suggest. The cold of space is not a destroying force. It is a preserving force. What it suspends, it holds. What it holds, it does not change. The cold is the most perfect archive there is. Everything the universe has ever made that found its way into the deep cold is still there, still the same, waiting for something warm enough and curious enough to find it and ask what it was. There is a specific detail about the experience of cold in the upper atmosphere that most people never encounter, and it illuminates something important about the relationship between altitude and temperature that is more complicated than it appears. The temperature of the atmosphere does not decrease uniformly with altitude. It decreases through the troposphere, the lowest layer where weather happens, reaching about minus 57 degrees Celsius at the tropopause, the boundary at about 12 kilometers altitude. Then it increases through the stratosphere as ozone absorbs ultraviolet radiation. Then it decreases again through the mesosphere. Then it increases again through the thermosphere, where individual gas molecules can have temperatures of thousands of Kelvin. A satellite in low Earth orbit is travelling through the thermosphere. The thermosphere has temperatures of 500 to 2000 Kelvin. A satellite in low Earth orbit is not warm. This is the same distinction we made about the interstellar medium. The temperature of a gas is the average kinetic energy of its particles. The number of those particles per unit volume determines whether they can transfer that energy to anything they encounter. The thermosphere has fewer than 1 billion molecules per cubic centimetre, compared to 27 quintillion per cubic centimetre at sea level. The thermosphere cannot warm a spacecraft. The spacecraft loses heat by radiation and, in the absence of any internal heat source, cools toward the background. The coldest natural temperature in Earth's atmosphere occurs in the mesosphere, around 85 kilometers altitude, over the poles in summer, where temperatures can reach minus 130 degrees Celsius. Cold enough for clouds to form, the noctilucent clouds that are visible from the ground at high latitudes during summer twilight, thin and luminous at the very edge of space. These clouds form when water vapour, present in the upper atmosphere in tiny quantities, freezes onto meteor dust particles. They are the highest clouds in the atmosphere, and they form in the coldest part of the atmosphere, not despite being near space, but because of the unique thermodynamic conditions that altitude and summer solar illumination create at that specific layer. The layers of Earth's atmosphere are not simply getting colder and colder as you go up. They are temperature layers, each maintained by the interaction between solar radiation, photochemical reactions, and the dynamics of the atmospheric circulation. The cold at high altitude is real, but it is not the cold of space. It is a pocket of cold created by the specific physics of the mesosphere, different in nature from the cold of the interstellar medium or the cosmic background. This matters because it means that the coldest thing accessible from the Earth's surface, the cold that noctilucent clouds are made of, is still warmer than the cold of the permanently shadowed lunar craters, which is still warmer than the Boomerang Nebula, which is itself warmer than the Hawking temperature of a stellar black hole. There is a hierarchy. There is always something colder. The floor goes down and down and down, and the bottom of the floor is the question of what the cold actually means, what it costs, and what, if anything, survives it. Antarctica is the coldest place on Earth. At Vostok Station, on the high East Antarctic Plateau at 3,488 meters elevation, the temperature reached minus 89.2 degrees Celsius on July 21, 1983. That record stood for decades. More recent satellite data has found locations on the Antarctic Plateau with radiative surface temperatures below minus 94 degrees Celsius on clear winter nights. These are not air temperatures measured in the standard way. They are the temperature of the surface itself radiating into the cold, clear sky above. But they tell you something about the thermal environment of the driest, coldest, highest, most remote continent on Earth. At minus 89, things behave in ways that do not occur elsewhere on the planet. Carbon dioxide at standard atmospheric pressure sublimes at minus 78 degrees Celsius. Below that temperature, CO2 in the atmosphere begins to condense and deposit as dry ice. At Vostok, in the coldest winter nights, traces of CO2 frost can form directly from the air. Diesel fuel freezes. Standard lubricating oils become unusable. Rubber becomes brittle and shatters. Electronic displays fail. The chemistry of cold, below minus 70 or so, starts operating outside the parameters for which most technology was designed. And yet, Antarctica is home to the largest astronomy installations in the Southern Hemisphere, to deep ice core drilling programs that recover climate records from hundreds of thousands of years ago, to bases where humans have lived continuously, in winter isolation, cut off from any possibility of evacuation for decades. The cold does not prevent human activity there. It demands specific technology, specific training, specific planning. But the activity happens. The South Pole Telescope sits at the geographic South Pole, at an altitude of 2,835 meters, in temperatures that regularly reach minus 60 in winter. It observes the cosmic microwave background, the 2.725 Kelvin radiation from the Big Bang, measured from a continent where the ambient temperature is minus 60 on a warm day. The telescope, looking at the coldest light in the universe, operated from the coldest place humans have chosen to build large-scale scientific infrastructure. There is a specific kind of clarity that comes with extreme cold, in both senses. The atmosphere over Antarctica is extraordinarily dry. The lack of water vapour means almost no atmospheric turbulence in the millimetre, wavelengths the South Pole Telescope uses. The observations are cleaner there than almost anywhere else on Earth. The cold that makes the site difficult to operate is the same property that makes it scientifically superior. The obstacle is the advantage. The hardship is the capability. This is not unique to Antarctica. It is a theme that recurs throughout the history of cold-related science. The cold that makes things difficult to operate in is often the cold that makes observations possible. The cold that kills careless explorers is the cold that preserves ancient climate records in ice cores. The cold that freezes equipment is the cold that keeps the dark matter detectors free from thermal noise. The cold does not care what you need it for. It simply is what it is. In 2016, about a mile beneath the surface of South Dakota, inside a former gold mine now converted to a physics laboratory, a team of scientists began filling a detector with 10 metric tons of liquid xenon cooled to minus 95 degrees Celsius. They called it Lux Zeppelin, or LZ. They were looking for dark matter. Dark matter accounts for roughly 27% of the mass-energy content of the universe. We know it is there because of what it does to the things we can see. Galaxies rotate too fast for their visible mass. Galaxy clusters bend light more than their visible mass would predict. The cosmic microwave background has specific patterns that require a cold, non-interacting form of matter that does not couple to light. Every line of evidence points towards something massive and invisible that fills the universe and holds it together. We have never directly detected a single particle of it. The leading candidate for dark matter is a class of hypothetical particles called WIMPs, weakly interacting massive particles. If WIMPs exist, they interact with ordinary matter through the weak nuclear force, just rarely. Very rarely. About once every few years, a WIMP should bump into an atomic nucleus in a sufficiently large and sensitive detector, producing a tiny nuclear recoil. To detect that recoil, you need a large target mass, a very sensitive detector, and an extraordinarily quiet environment. Hence the liquid xenon, deep underground, behind shielding designed to stop every other kind of particle that might mimic a WIMP signal. The xenon is cold for a reason. At minus 95 degrees Celsius, it is liquid and dense, providing a large number of target nuclei per cubic meter. When a particle recoils in the liquid xenon, it produces a flash of ultraviolet light and a cloud of electrons. The light and electrons are detected, allowing physicists to reconstruct the position and energy of the recoil and distinguish a potential WIMP signal from radioactive background noise. LZ ran its full first experimental campaign and found no convincing dark matter signal. The detector worked. The sensitivity was unprecedented, the data was clean, and the dark matter was not there, at the cross-sections the most popular models had predicted. This is the frontier of cold physics meeting the frontier of cosmology. A detector at minus 95 degrees, a mile underground, searching for particles that make up 27% of the universe by mass. Not finding them. Pushing the experimental limits further and further into the territory where, if WIMPs exist at the expected cross-sections, they should already have been seen. The cold does not yield its secrets easily. Dark matter passes through the xenon, through the mountain above it, through the Earth itself, through your body, trillions of particles per second, by the best estimates. Vast, cold, invisible, everywhere, and undetectable by every method we have so far tried. The cold of the detector is an attempt to quiet the universe enough to hear the whisper. So far the whisper has not come. The coldest inhabited places on Earth give you some sense of what the lower limit of human tolerance actually is. Not the survival limit, which is different, but the limit of sustained habitation, of living, working, raising children, getting through winters. Oymyakon in eastern Russia holds the record for the coldest permanently inhabited place. In February 1933, a temperature of minus 67.7 degrees Celsius was recorded there. It is a village of roughly 500 people, located in the valley of the Indigirka River in the Sakha Republic, at about 63 degrees north latitude, which is roughly the latitude of Fairbanks, Alaska. The valley geography traps cold air. The long winter nights allow the temperature to drop without the interruption of solar warming. The landscape is permafrost, soil that has been permanently frozen for thousands of years, through which liquid water can only be obtained from geothermal springs. At minus 67, most technology fails. Car engines must be kept running continuously, or they will not restart. Metal becomes brittle at temperatures below about -40, and parts that would flex at room temperature shatter. Glass's frames freeze to the skin they touch. Eyelashes freeze together. Breathing in without covering your nose and mouth risks frosting the airways. And yet, people live there, have lived there for generations. The Yakut people developed clothing and building techniques, ways of keeping animals alive, methods of obtaining food and water that allow sustained habitation in a climate that would kill an unprepared person in hours. The adaptations are cultural and technical rather than biological. Modern humans are not physiologically adapted to these temperatures the way polar bears or Arctic foxes are, but the adaptations are real and they work. There is something clarifying about this. The limits of human tolerance for cold are not where our biology puts them. They are where our technology and culture put them. With the right gear, the right shelter, the right food, the right knowledge, humans can survive at temperatures that would otherwise be immediately lethal. The range of environments we have colonized through technology dwarfs the range our biology could tolerate without it. This is the same principle that allows humans to survive in the vacuum of space, in the depths of the ocean, in the deserts of Antarctica. Not biological adaptation, engineering. The spacesuit, the diving suit, the polar sleeping bag, the insulated buildings and the geothermal heating systems of Oymyakon, all of them are the same idea applied at different scales. You cannot make yourself cold tolerant. You can build something around you that manages the cold so your narrow biological range is preserved inside it. The cold of space, -270, -273, is so far beyond the range of anything in human experience that the engineering required to survive it indefinitely does not yet exist in any robust form. We have been to the moon, briefly. We have kept people alive on the International Space Station continuously since 2000. But long-term habitation in the open thermal environment of deep space, without the warmth of Earth or a nearby star, is a problem we have not solved. The cold we manage on Earth is a prelude. The cold we would need to manage in the outer solar system or in interstellar space is a different order of problem. The gap between -67 and -270 is not just 203 degrees. It is civilizational. There is a specific way that the cold of space intersects with time that is rarely discussed and almost never fully absorbed. When you look at a star, you're seeing light that left it some time ago. The sun's light takes 8 minutes to reach us. The nearest star system, Alpha Centauri, is about 4 light-years away, meaning the light we see from it left 4 years ago. The stars in the night sky that are visible to the naked eye range from a few light-years to a few thousand light-years away. The Andromeda Galaxy, visible as a smudge in dark skies, is 2.5 million light-years away. The light we see left it 2.5 million years ago, when Homo sapiens did not yet exist. This temporal displacement has a thermal component. The universe is cooling, not quickly by human timescales, but consistently. The cosmic microwave background today is 2.725 Kelvin. When the universe was half its current age, it was warmer, roughly 4 Kelvin. When the universe was 1/10 its current age, the background was 27 Kelvin. When the universe was 380,000 years old, at the moment of recombination when the background was released, the temperature was about 3000 Kelvin. The background we detect today is not just old, it is cooler than it was when it was created. 13.8 billion years of expansion have stretched it to colder wavelengths. Looking out into space is looking back in time, and looking back in time is looking at a warmer universe. The most distant galaxies visible in deep field images from the Hubble and James Webb telescopes formed when the universe was less than 1 billion years old, when the cosmic background was 10 to 20 Kelvin, several times warmer than today. The first stars formed in a universe that was warmer than ours. The galaxies themselves were warmer, more active with star formation, more densely packed with the raw material of new suns. The universe we observe in the deep past is a hotter, more energetic version of the universe we observe locally. We are living in a universe that is cooling, not the way a cup of coffee cools in minutes, in a way we can watch. The way a civilization might cool over spans of time so vast they exceed our ability to conceptualize them. The universe today is cooler than it was when the Milky Way formed. It will be cooler still when the sun burns out. The cooling does not stop. It cannot stop, because the second law of thermodynamics does not allow energy differences to persist forever. Every temperature gradient in the universe, every hot thing next to a cold thing, is a temporary condition. The direction of evolution is always toward equalization, toward the uniform cold of heat death. We are not at the beginning of this process. We are somewhere in the middle. The universe is already cold enough that most of its volume is inhospitable to life as we know it. It is not yet cold enough for the last stars to burn out, the last black holes to evaporate, the last temperature gradients to equalize. We're in the warm, active middle period, which will be followed by a long, long cold. The cold is not coming. The cold is here. We are just warm enough briefly to notice the difference. The vacuum of space is not cold in the way that the word cold is normally used. Vacuum has no temperature. Temperature is a property of matter, specifically a measure of the average kinetic energy of particles. A vacuum is the absence of matter. It cannot be hot or cold in itself. What makes space cold is what happens to objects placed in it. An object in space has no medium to exchange heat with by conduction or convection. It can only exchange heat by radiation. It radiates its own thermal energy outward as infrared light, and it absorbs radiation from its surroundings. If its surroundings are at 2.725 Kelvin, the cosmic microwave background, and there is no nearby star or other warm object, then the only radiation it absorbs is that of the background. Since the object is almost certainly warmer than 2.725 Kelvin, it radiates more than it absorbs. Its temperature falls. It cools toward 2.725. The rate of cooling depends on the object's properties. The Stefan-Boltzmann law relates the power radiated by a surface to the fourth power of its temperature. An object at 300 Kelvin radiates about 459 watts per square meter. An object at 30 Kelvin radiates about 0.046 watts per square meter. An object at 3 Kelvin radiates about 0.0046 watts per square meter. The cooling slows dramatically as the temperature drops, because the radiation rate falls so steeply with temperature. An object near 2.725 Kelvin barely radiates at all, barely absorbs at all, and the equilibrium is approached asymptotically, never quite reached, but approached. This is why cold storage in space is, in principle, possible over enormous timescales. An object at 2.725 Kelvin in stable equilibrium with the cosmic background does not change. The rate of chemical reactions near absolute zero is essentially zero. Biological processes, even microbial life, cannot operate below about -20 Celsius, 253 Kelvin. An object at 2.725 Kelvin is 250 degrees below even the most cold-tolerant biology. It is preserved, not alive, but preserved in the sense that the atoms and molecules that make it up are not going anywhere, not reacting with anything, not changing in any significant way, over timescales limited only by the slow processes of cosmic ray damage and radioactive decay. The cold of space is a preservative. What is frozen in that cold is held in place. This is why the icy bodies of the outer solar system, the comets and Kuiper belt objects, and the Oort cloud at the far edge of the solar system carry chemistry from the early solar system largely intact. They have been cold enough for long enough that the organic molecules and water ice and complex chemistry they contain is preserved from the era of planetary formation, 4.5 billion years ago. Every comet that falls inward from the outer solar system is, in a sense, a time capsule. The cold made it so. The cold that seems to be the opposite of life, the cold that makes the outer solar system uninhabitable by any biology we know, is the same cold that preserved the chemical record of the solar system's formation for 4.5 billion years, waiting for someone warm enough and curious enough to open it and read what was inside. There is a thought experiment worth sitting with. Imagine you're in interstellar space, far from any star, in the space between the spiral arms of the Milky Way. Not at the edge of the galaxy, not in a void between galaxies, just in the ordinary interstellar medium, the kind of space that makes up the vast majority of the volume of our galaxy. You have survived the trip somehow. You're in a pressure suit, well insulated, with oxygen, with a heat source keeping you warm. You look around. What you see first is nothing. Not dark in the dramatic movie sense where darkness has texture and menace. Nothing. The density of stars visible to the naked eye in interstellar space, away from the galactic plane, is lower than it is from Earth. The Milky Way is a pale band, stars too distant to resolve individually, a diffuse glow. There are no nearby stars, no sun, no planet. The nearest star might be 2 or 3 light years away. At that distance it is a point of light, bright for a star, but a point providing no warmth, no radiation of any significance. What you cannot see is the cold, 2.725 Kelvin in every direction equally. The cosmic microwave background, photons with wavelengths of about a millimeter, arriving from every direction with the same intensity. You cannot see them with your eyes. They are in the microwave range. But they are there, bathing you, passing through your suit, absorbed by the outer surface of your suit, re-radiated back towards space. Your suit is warmer than 2.725 Kelvin. It is losing heat slowly to the background. Without a heat source, it would cool toward that temperature, slowly, over days or weeks, depending on the insulation and the thermal mass, but certainly. The heat source in your suit is running. The cold is being held at bay by the engineering between you and it. The engineering is the only thing between you and 2.725 Kelvin. Look at your hand inside your suit. The heat in it is maintained by metabolism, by blood circulation, by the thermoregulatory response of your body to the cold outside. Remove the suit, and you would lose consciousness from hypoxia in under 2 minutes, before the cold even became the primary concern. Keep the suit and the heat source, and you are, for the moment, one of the few warm things in several cubic light-years of interstellar space. How large a warm thing are you? Your body generates roughly 100 watts of metabolic heat. The sun generates approximately 3.8 times 10 to the power of 26 watts. You are, thermally speaking, about 40 quadrillion times less significant than the sun. In interstellar space, your warmth is too small to matter to the thermal structure of anything around you. You are warm, and you are nothing. But you are warm, and you are aware of the cold. That combination, warmth and awareness, is the thing that is rare. The cold is ubiquitous. The warmth is common enough in the aggregate that stars exist. The awareness is the thing we do not have a good count on. The awareness is the part that makes tonight's conversation possible. The cold is the context. The awareness is the point. The discovery that the universe is not just cold but getting colder was not expected when it was made. In 1998, two independent teams of astronomers, one led by Saul Perlmutter and one by Brian Schmidt and Adam Rees, were measuring the distances and recession velocities of Type Ia supernovae in distant galaxies. Type Ia supernovae have a consistent intrinsic brightness, making them useful as standard candles for measuring cosmic distances. By comparing the apparent brightness of supernovae in distant galaxies to their redshift, you can infer how the expansion of the universe has changed over time. The expectation was that the expansion would be slowing down. Gravity, after all, pulls matter together. The gravity of all the matter in the universe should be decelerating the expansion set in motion by the Big Bang. The supernovae should appear slightly brighter than they would in a universe that was not decelerating, because the distant galaxies would not have moved as far as expected. Instead, the supernovae appeared slightly fainter. They were farther than expected. The expansion was not decelerating. It was accelerating. Something was pushing the universe apart, working against gravity, driving the expansion faster and faster over cosmic time. This something, unknown in its nature, came to be called dark energy. The measurements earned Perlmutter, Schmidt and Rees the Nobel Prize in Physics in 2011. Dark energy accounts for roughly 68% of the total mass energy content of the universe. The accelerating expansion has direct implications for the ultimate cold of the universe. If the expansion continues to accelerate, distant galaxies will eventually be moving away from us faster than light can travel between us and them. They will become causally disconnected. The observable universe will shrink over time, not in physical size, but in the number of objects with which we can exchange light and information. Galaxies that are currently visible will eventually redshift into invisibility, their light arriving too cold and too faint to detect. The cosmic background will redshift to even lower temperatures. The universe will become darker and colder as the expansion carries most of its content beyond any possible reach. This is the future that the data points toward, not the heat death of uniform temperature across a static universe, something lonelier. A universe still expanding, each region cooling in isolation, the connections between regions severing one by one as the expansion carries them beyond the speed of a light horizon, an increasing cold and an increasing isolation. The cold is not just a property of the present universe, it is the trajectory. Everything observable points in the same direction. More expansion, more separation, more cooling. The universe is not on its way to warmth. It was briefly warm, briefly active, briefly structured in ways that allowed stars and planets, and whatever we are. That brief period is now. It will not last. The cold is not coming. It is the direction everything is going. The dark energy that is accelerating the expansion is making the future colder faster than it would otherwise be. The universe is not coasting toward cold. It is accelerating toward it, driven by a force whose nature we do not understand, whose ultimate effect we can calculate even if we cannot explain it. The future is cold, and it is arriving faster than expected. That is what the supernova told us in 1998, and the data has not changed its story since. The night sky, properly understood, is a map of cold. The bright points are exceptions. Every star is a nuclear furnace, converting hydrogen to helium at millions of degrees, radiating energy outward in all directions. The night sky is full of these furnaces, hundreds of billions in our galaxy alone, and hundreds of billions of galaxies beyond ours. The sky appears to be rich with warmth. But look at what the stars are set against. The dark between the stars is not nothing. It is the interstellar medium, the sparse gas and dust that fills the space between suns, and the temperature of the interstellar medium, far from any star, is defined by the cosmic microwave background, 2.725 Kelvin. The dark between the stars is nearly as cold as anything gets. The ratio of warm stellar material to cold interstellar material by volume is roughly 1 to 100 million. For every cubic meter occupied by stellar plasma, roughly 100 million cubic meters are occupied by cold or near-cold interstellar gas. Most of the observable universe by volume is cold. Most of the observable universe by mass is dark. Dark matter, which does not interact with light, makes up roughly 27% of the total mass energy content. Ordinary matter, everything that shines or glows or can be detected by electromagnetic radiation, makes up roughly 5%. Dark energy accounts for the remaining 68%. The stars, the planets, the galaxies, the nebulae, the gas clouds, everything we have ever detected through any telescope is roughly 5% of what is there. The cold, the dark, the invisible. This is almost everything. The warm, the bright, the visible. This is a rounding error. There is a version of this fact that is meant to make you feel small, to point out that the observable universe is 93 billion light-years across, and most of it is cold and dark, and we're on a small rock orbiting a mediocre star in a medium-sized galaxy, and therefore our significance is vanishingly small. This is the dismissive version. It uses scale as a cudgel. The more honest version is stranger. Yes, we're on a small rock. Yes, most of the universe is cold and dark. But we are here, warm, and aware that it is cold and dark, and that awareness is a property of the universe that the cold darkness itself does not possess. The universe does not know it is cold. We know the universe is cold. That is not a small difference. That is, so far as we know, the entire difference between a universe that is merely physical and one that has something to say about itself. The cold is the rule. The warmth is the exception. The awareness of the difference is the rarest thing of all. We do not know how rare. We do not know whether awareness is unique to this planet or scattered across the galaxy, in places we have not yet found or heard from. We do not know whether the warm, structured, aware fraction of the universe is enormous or vanishingly small. We only know that we are part of it, that we are warm and aware, and that we can look out at the cold and name it. That naming is not nothing. That naming is tonight. Here is what it feels like to be genuinely cold, not discomfort, not the shiver of stepping outside without a coat, the deep cold that comes when the mechanism for dealing with cold begins to fail. The first thing to go is fine motor control. The fingers stop doing precisely what the brain tells them to do. Tying a knot becomes difficult, then impossible. This is peripheral vasoconstriction, the body redirecting blood toward the core to preserve core temperature at the cost of the extremities. The hands are cold because the body has decided the hands are expendable. The second thing is judgment. This is the insidious part. People who are dangerously hypothermic often do not feel particularly cold. The sensation of cold diminishes as the cognitive faculties that process it degrade. There are documented cases of people in late-stage hypothermia removing their clothes because they felt warm. Paradoxical undressing, it is called. The brain, as it cools, sometimes sends warmth signals. The body's last acts can include self-destructive behavior triggered by a thermoregulatory system that is failing in complex ways. The third thing is the slowing of everything. The heart rate drops, the respiratory rate drops, the metabolic rate drops. The body is doing less of everything, conserving the energy it has left for as long as possible. In cold water, this can happen quickly. In cold air, more slowly. But the direction is always the same toward the minimum, and then sometimes a reversal. People have been resuscitated from core temperatures below 14 degrees Celsius. The cold that was killing them also protected their brain from the damage that lack of circulation normally causes. The cold is a poison and an antidote simultaneously. It shuts the body down and slows the process of dying in the same stroke. Medicine has learned to exploit this. Therapeutic hypothermia, deliberately cooling patients after cardiac arrest, can reduce brain damage precisely because the cold slows all the rate processes, including the destructive ones. What cold is, at the biological level, is a throttle on the chemistry of life. Turn the throttle down far enough and the chemistry stops. But stopping the chemistry is not immediately the same as destroying the chemistry. The machinery is still there. The molecules are still in their relationships. The DNA is still encoded. The proteins are still folded. The information is preserved. This is the principle behind cryonics, the speculative practice of freezing bodies or brains after death, in the hope that future technology might reverse the damage and restore the person. The cold does not preserve life. It preserves structure. Whether structure is enough to preserve identity, whether the information encoded in a frozen brain is the information that constitutes a person, is a philosophical question that neither biology nor physics has answered. What is not in question is that cold preserves. The permanently shadowed craters of the moon hold water ice from 3 billion years ago. The permafrost of Siberia holds mammoths frozen with their last meal still in their stomachs. The interstellar medium holds prebiotic chemistry from before the solar system formed. The cold preserves. It does not animate, but it preserves. Let the pace slow down a little now. The information has been coming fast. The numbers have been large and various, jumping from 2.725 Kelvin to -89 at Vostok to 1 Kelvin at the Boomerang Nebula to 170 nanokelvin in a Colorado laboratory. Let them settle. What is the cold when you have put all the numbers away and let them find their proper place? The cold is the default. The universe left to itself, without the ongoing intervention of nuclear fusion in stars, without the residual heat of planetary formation, without the metabolic chemistry of living organisms, returns to the cold, not instantly, not violently. With extraordinary patience, at a rate that makes geological time look hurried, but returns. Everything returns. The warmth in this room, right now, is the product of chains of energy transfer that trace back ultimately to nuclear reactions in the core of the sun. The sun converted some of its hydrogen to helium and released energy, which radiated outward and was absorbed by the Earth's surface and atmosphere, which heated the air, which warmed the building you're in, which is keeping the air around you from cooling to the outdoor temperature. Cut any link in that chain, and the warmth begins to dissipate. The chain has been running for 4.6 billion years. It will run for another 5 billion, roughly, before the sun exhausts its hydrogen. Then the chain breaks. After the sun is gone, nothing about the Earth is cold-proof. The residual heat of the cooling Earth's interior will keep the core liquid for some time, will drive some residual volcanism, but the surface will freeze. Without solar heating, and without an atmosphere to retain whatever heat remains, the surface temperature of the Earth will trend toward the temperature of the space around it, toward 2.725 Kelvin, slowly, over millions of years, but toward it. Everything in the solar system will eventually be as cold as the space it orbits in. This is not a cause for despair. It is information. It is the universe being honest about what it is. Most of it is cold. A small fraction of it is warm, temporarily, due to ongoing nuclear reactions in stars. An even smaller fraction of it is warm and structured and aware, due to the specific chemistry that a particular kind of warmth supports under specific conditions. That fraction is what you are. the warm, structured, aware fraction. The cold is the vast majority. The warmth is the local, temporary exception. But the exception is where everything interesting has happened. Every piece of art that has ever been created, every scientific discovery, every relationship, every conversation, all of it happened in the exception. All of it depends on the ongoing maintenance of the exception against the rule. The cold is not the enemy. The cold is just the universe being what it mostly is. The warmth is you, being what you mostly are. This is the right place to slow down, to let the cold be large and the warmth be specific and temporary and real. If you went outside tonight and lay on the ground and looked at the sky for long enough, something would shift, not emotionally, thermally. You would begin to lose heat, not to the air necessarily, to the sky. This is a process called radiative cooling, and it is the reason clear nights are colder than cloudy nights, and the reason frost forms on clear nights even when the air temperature is technically above freezing. The ground, and everything on it, radiates heat upward as infrared light. On a clear night, that radiation escapes through the transparent atmosphere to space. On a cloudy night, the clouds absorb the radiation and radiate some of it back. The clouds are warm relative to space. Clear sky is cold relative to clouds. When you radiate heat upward into a clear sky, you're radiating into the cosmic background, into 2.725 Kelvin. The actual effective radiative temperature of the clear sky on a cold, dry night can drop to around -20 to -30 Celsius, much colder than the ambient air temperature. This is why your car windshield frosts up overnight even when the air temperature is above zero. The glass is radiating to the cold sky and cooling below the dew point. You are doing the same thing. Right now, if you are in a room, you are radiating infrared light in all directions. The walls absorb it and radiate it back. The temperature of the room and the temperature of the walls are similar, so the exchange is roughly balanced. You are in equilibrium with your immediate environment. Go outside on a clear night and the balance shifts. You radiate upward into the cold sky and the sky radiates almost nothing back. Your outer surface begins to cool. Your thermoregulatory system compensates. Your body redirects blood from the periphery to the core, generates additional heat through shivering if necessary, sends the signal to put on a coat. The coat is, fundamentally, a shield. It traps a layer of warm air against your body and prevents the infrared radiation from your skin from reaching the cold sky directly. It makes your immediate thermal environment warmer by creating a boundary between your warm surface and the cold night. The coat is doing exactly what the atmosphere does for the Earth, what the ice shell does for the ocean of Enceladus, what the sun shield does for the James Webb Space Telescope. It is a thermal management system, separating a warm interior from a cold exterior by means of a barrier that slows the heat loss. Everything that is warm in this universe is wrapped in something that slows the heat loss. The star is wrapped in the gravity that keeps the fusion reaction going. The planet is wrapped in its atmosphere. The organism is wrapped in its skin and clothing and shelter. Unwrap any of these and the cold comes in, not instantly, but inevitably. The cold is outside every warm thing. Always. The barrier is what you are. The barrier is what everything alive is. There is a place colder than the void between galaxies, and it was made in a laboratory in Boulder, Colorado, and it was made by pointing lasers at atoms. Laser cooling was developed in the 1980s. The principle is counterintuitive to the point of seeming like a joke. Lasers, which are associated with heat and cutting and burning, are used to cool things. The mechanism works because of the momentum carried by photons and the Doppler effect. A laser tuned to a frequency just below an atom's absorption frequency will be absorbed preferentially by atoms moving toward the laser. Because their motion blue shifts the laser's frequency into resonance. Each absorbed photon gives the atom a tiny momentum kick in the opposite direction to its motion. Over millions of cycles of absorption and emission, the atoms slow down. They cool. With multiple lasers aimed from all directions, the atoms in a small cloud can be slowed in all directions simultaneously. The cloud reaches temperatures in the microkelvin range, millionths of a Kelvin. Further cooling to nanokelvin temperatures uses a different technique. The trap depth is gradually reduced, allowing the most energetic atoms to escape. The remaining atoms re-equalize at a lower average energy. The coldest atoms remain. The process repeats. The temperature falls. At 170 nanokelvin, which is where Cornell and Wieman arrived in 1995, something fundamental changes. The atoms can no longer be described as individual particles. Their quantum mechanical wave functions, the mathematical objects that describe their position and momentum as probability distributions, become large enough to overlap with the wave functions of neighboring atoms. The atoms lose their individuality. They merge into a single quantum state, a Bose-Einstein condensate, behaving as one entity. This is the weirdness that lives at the bottom of cold. Not the ordinary weirdness of quantum mechanics that operates at atomic scales and is safely invisible in daily life. A visible, macroscopic weirdness. A cloud of atoms large enough to see with a naked eye, exhibiting quantum behavior that should only exist at subatomic scales. Superfluidity, coherence, interference fringes from matter waves, the same kind of interference you see when two water waves cross, but produced by clouds of matter cooled to a temperature that does not naturally occur anywhere in the observable universe. The cold is not just a gradient towards zero. The cold is a boundary, above which matter behaves in familiar ways and below which it does not. The boundary is not sharp. It occurs at different temperatures for different materials and different phenomena. But it is real. The universe has, written into its physics, a regime where the familiar rules break down and the quantum weirdness takes over. The regime is accessible only at temperatures that do not occur in nature. We found it by cooling atoms with lasers. The coldest things in the known universe are human-made, and they are strange in ways that nothing at ordinary temperatures can be. The bottom of cold is not emptiness. It is a place where the physics changes. There is one more thing the cold does that we have not talked about yet. The cold ends things, but it also begins them. Every star in the night sky began as a molecular cloud, a region of the interstellar medium where the density was high enough and the temperature low enough for hydrogen molecules to form and survive, 10 to 30 Kelvin, slowly contracting under gravity, slowly increasing in density, slowly increasing in temperature as the gravitational potential energy converted to heat. The cloud collapses. At the center of the collapse, where the density becomes high enough for the gas to be opaque to radiation and heat can no longer escape, the temperature rises rapidly. Eventually, hundreds of millions of Kelvin at the center, sufficient to ignite nuclear fusion. A star is born. The cold is the starting condition. The cold molecular cloud sitting at 10 Kelvin in the interstellar medium is the raw material from which stars form. Without the cold, without the temperature low enough for hydrogen molecules to form and for the cloud to be stable against thermal pressure, the collapse cannot happen. The warm interstellar gas cannot form stars. Only the cold can. The same principle applies to planets. The solid particles in the outer solar system, the ice and rock that aggregated into the planetary cores of the gas giants, formed in the cold outer regions of the solar nebula, where the temperature was low enough for water and methane and ammonia to freeze. The frost line, the distance from the young sun at which water ice could condense, was roughly where the asteroid belt is now. Inside the frost line, the material was rocky and dry. Outside it, where it was cold enough for ice, the material included a much larger mass of frozen volatiles, enabling the formation of the massive cores that then accreted hydrogen and helium to become the gas giants. Jupiter and Saturn, the largest planets in the solar system, exist because the outer solar system was cold enough for ice to form. The cold that makes the outer solar system uninhabitable is the same cold that made the giant planets possible. This pattern recurs at every scale. The cold molecular clouds that seem like death zones, places where no life could survive, are the nurseries of the stars that make life possible around them. The cold outer solar system that seems like the antithesis of life's conditions is where the most volatile chemistry of the early solar system was preserved, and where the building blocks of potentially habitable ocean worlds survive today. The cold is not the opposite of the warm. The cold is the condition that makes certain kinds of warmth possible. The cold makes the collapse happen. The collapse makes the heat happen. The heat makes the light happen. The light makes you happen. You're a consequence of cold that collapsed. The cold that surrounds you, that presses on every warm thing in the universe, is not the end of the story. It is the beginning of it. The night is getting late now. Or early, depending on when you're doing this. The numbers that have come out tonight are real. The cosmic background at 2.725 Kelvin is real. The permanently shadowed craters at 40 Kelvin are real. The Boomerang Nebula at 1 Kelvin is real. The Bose-Einstein condensate at 170 nanokelvin is real. The heat death of the universe is a real prediction from real physics, not a metaphor, not a hyperbole. These are the actual conditions of the actual universe you live in, and here is what that means for the room you are sitting in right now. The air around you is warm because the sun is warm. The sun is warm because it is converting hydrogen to helium in its core at a rate of 4 million tons per second. It has been doing this for 4.6 billion years. It will do it for approximately 5 billion more. Every degree of warmth you have ever experienced in your life, every fire, every warm day, every heated room, every warm meal, traces back ultimately to nuclear reactions in the sun. The sun is the reason the Earth is warm enough for liquid water. The Earth's atmosphere is the reason the sun's warmth is retained overnight instead of radiating back to the cold. Your body's metabolism is the reason you are warmer than the room, warmer than the outside air, warm enough to function. Remove any of these things and the cold comes in. Not dramatically, not all at once, but inexorably, at a rate that physics determines, toward the 2.725 Kelvin that the universe offers by default when nothing is working against it. Everything you are, everything you experience, the texture of warmth and the possibility of thought, and the structure of chemistry that makes biology possible, all of it is maintained by the ongoing, uninterrupted work of a star 150 million kilometers away. The cold does not have to do anything to eventually win. It just has to wait. And it has been waiting at 2.725 Kelvin since the universe was 380,000 years old. But the waiting is on timescales that make the word patient feel inadequate. The sun has 5 billion years left. In 5 billion years, every star that has been named and catalogued in human history has a reasonable chance of still being burning. The Earth has been around for 4.6 billion years. In 5 billion more years it will still be orbiting whatever the sun becomes. The timescales on which the cold wins are timescales on which the present moment is so brief as to be immeasurable. You are warm, right now, in a universe that is mostly cold. That warmth is real and specific and maintained by a chain of processes that is currently unbroken. The cold is real and vast and patient. Both things are true simultaneously. Both things are exactly as large and as small as they are. The cold is not a reason for despair. It is a reason for precision, for knowing what the warmth actually is, where it comes from, how long it lasts, and what it makes possible in the time it has. It makes you possible. Tonight, at whatever temperature your room is, at this hour, you stayed. Not everyone does. The cosmic microwave background and the Boomerang Nebula, and the heat death of the universe and the Bose-Einstein condensate, and the 2 degrees of hypothermia at which judgment first fails. It is a lot of cold, a lot of numbers, a lot of space between the warm things. But you stayed, which means you went all the way to the place where the numbers stop feeling like information and start feeling like context, where the room around you stops being just a room and becomes a specific, maintained exception to a rule that applies almost everywhere else, where the warmth stops being incidental and becomes the whole point. That is the thing tonight was trying to give you. Not fear, precision, the precise understanding of what cold is and where it lives and how vast it is and why the warmth is specific, and how the cold, at the deepest bottom of it, is where the physics changes and where the stars begin and where the chemistry of life was assembled in the dark over millions of years at 10 Kelvin on the surfaces of dust grains drifting between the stars. The cold made you. The cold is waiting for you. In between, there is this, the warm exception, the specific brief interval of warmth and structure and awareness that looks out at the cold and names it and measures it and writes it down. Before you close this out, one thing. Leave a comment. Not an essay, just your city and the time, that is it. Because one of the things tonight was about is knowing where the warm places are, and you are one of them, and you're at a specific coordinate right now, reading this, warm, at a specific hour, and I want to know where you are. The city and the time are enough. The comment section, when it fills up with names of cities and hours of the night and early morning, becomes a small map of warm places in the cold universe. That is worth making. If this did what I hoped it did, the like button and the subscribe button are there. They do one thing. They send this to the next person, in the next city at the next hour, who might need to understand the cold the way you now understand it. That is all. That is the whole ask. The cosmic microwave background is passing through you right now at 2.725 Kelvin. The Boomerang Nebula is 1 Kelvin, 5,000 light-years away, colder than anything the universe makes except in the most extraordinary circumstances. The heat death is coming, at a remove of time that makes the current age of the universe negligible. The dark matter is passing through you by the trillions per second, cold and invisible and real. And you are warm, at this specific hour, in this specific city. One of the warm places in the cold universe, reading about the cold from inside the exception, aware of what the exception costs and what it makes possible, and how long the cold has been patient and how brief the warmth is and how real both of them are simultaneously. That is what tonight was. Good night.